then yesterday night the report has come, both of them are corona positive. So she came to department yesterday with her son and also did some official work, tasked some papers and all this. And then finally yesterday night, the report has come that she is corona positive, she and her son both. So today department is actually totally under lock and key. And the university has totally locked the department and sanitization work is going on. So I take the class from the department. As you can see that I take the class from department in the board. So with lot of requests I could enter just for the class. And after the class I will also go and they will lock the department, the gate of the department. Nobody can enter. So that's why I requested all of you that please join a little early so that I can complete the class by 11:50, because a person is waiting downstairs with a lock and key that as I will complete the class, he will lock the department. So this is the background for which I requested all of you to join a little early at 9:45 so that I can start the class. Okay, so let me start the class because many are already joined. Now, where I actually completed yesterday, and a little hurriedly actually I completed, that is the kurtosis, the discussion of the kurtosis of the sediment. And there I actually discussed the kurtosis. It is actually 595 minus 55 by 2.44 into 575 minus 525. This is what I discussed, that this is actually what kurtosis is actually referred to as kg kurtosis. That is how kurtosis is referred. And then we say that how is the distribution between the extreme and the middle part. They are relative nature, that if I have a middle part is more pronounced and the end part of the tail part they are negligible, then you call it a leptokurtic or you call it a bradycardic. So this is the thing what I tried to say in the yesterday class and when we were completing the class. Now, once I have already discussed the mean, median, mode, sorting, skewness, kurtosis, all these statistical parameters, then the question comes, what we will do with these parameters? How these parameters will help us in different kind of interpretation. So first of all, we discussed how we measure the grain size, how we measure a pebble, cobble, sand, or a silt or a mud size grain. That we have discussed. Then we have discussed, once we measure the grain size, what kind of plot we do and what kind of data we generate out of it. Now the question comes, what we will do with that data? So what interpretation we actually do? So the interpretation of data, that is of different kind. Number one, can it give us any idea about the source of the sediment, character of the source of sediment? Can it give us any idea about the source, character of the source of the sediment? Number two, can it give us any idea about the transportation of the sediment? Transportation of the sediment. And number three, can it give us any idea about the depositional environment of the sediment? Depositional environment of the sediment. So there are threefold the question. Questions are threefold. That what the data I have generated, what kind of idea it can give from about the source area, or what kind of idea it can give about its transportation history, or what kind of idea it can give where the sediment finally got deposited, what is the kind of depositional environment, can it give any idea about that? So all the ideas that is basically from the whatever we have generated, the mean, median, mean. So our next discussion will be on this slide. our next discussion will be on this. So first start with the source of the sediment. Source of the sediment. Now, when the data, that is, people observe certain very funny things. What is that? That when globally the data, that what kind of sediment I am getting from different kind of environment. Suppose it is from shallow marine environment, from fluvial environment. So any kind of environment, when they tried that we should get the data, then they found that the sum of the grain sizes, they are very ill represented. That is 4 to 2 mm, 4 to 2 mm, 2 to 1 mm, 2 to 1 mm, and 1 by 16 to 1 by 32 mm. These grain size are not represented much. You just think of the amount of sand you basically we get is a sediment. Do we get the same amount of silt? No. Silt is very rarely seen. Now, these grain sizes, that is not well represented from the natural environment. It is not that all this data, what I am talking about, the 2 to 2 mm, 2 to 1 mm, 1 by 16 to 132 mm, these they did mostly from the fluvial sandstone, from the river deposited sandstone, from the river deposited sandstone. Then they did it also from the shallow marine sandstone, What they see in the shallow marine, they found that 4 to 2 mm and 1 by 8 to 1 by 16 mm, these grain sizes are very rare. Coarser than that, they are getting. Finer than that, they are getting, but these grain sizes are not there. Then they carried it out in the aeolian sediments also, air-driven sediment. It is the same observation in the air-driven sediment also, that some of the grain size are not very well represented. And then when it was found, then the question came in the mind of people, are these grain sizes not generated in the source? These grain sizes, possibility, what can be the possibility? Why I am not getting these sizes as I am getting the other sizes? Why I am not getting these sizes are ill represented? The possibility what came to the people's mind is that these grain sizes not generated in provenance. That is one possibility. Not generated in provenance. Second possibility is that these grain sizes during transport they are getting separated. And not finally reaching to the depositional site. So during transport, they are hydrodynamically separated, and they are not reaching to the depositional site. And the third possibility that came into the mind of people, is that during transport, these grain sizes they get further fragmented. Fragmented during transport, and hence change their size. Is it clear what I am saying?
Yes, sir.
So there are three different possibilities that these grain sizes are not generated in the provenance. They are hydrodynamically separated and thereby not reaching the depositional site. And third is these grain sizes, they are getting further fragmented so that these sizes finally not reaching to that. Now, then the question comes, then out of this, which one is most valid? Valid, and what I should be actually concluding as the reason behind the less representation of some of the sizes. That grain size is not generated in the provenance. What is the reason behind it? If I have suppose there is some bias, I do fully agree. There is some, suppose an acidic rock, a granitic rock, when it will be basically creating the sediment, it will create the quartz grain, it will create the feldspar grain, and the feldspar they will be decomposing, and they will, with the deeply rooted weathering profile, the feldspar will also give the clay mineral. So a granite will give you both. A granite will give you both quartz, feldspar, and clay mineral. But what about a basic rock? A basalt? A basalt can only give you the clay mineral or the lithic clast. Lithic clast. Just one question to all of you. What is a lithic clast? That is a rock clast. Rock clast. What is quartz? What is feldspar? They are mineral grade. When I talk about lithic clast, that is a rock clast. Now, if I get the lithic clast in a sediment, what kind of provenance I normally interpret? If lithic clast is dominant in a sandstone, then what kind of provenance I interpret? Should I interpret a acidic granitic provenance or I interpret a basic provenance?
So basic provenance.
Why?
So because acidic rock tend to, so they are much brittle and they tend to dissociate in.
Acidic rock? Acidic rock?
So they dissociate into their grains. They do not tend to dissociate into lithic class. So it's written in JD Winter.
No, why? The reason is that the acidic rock are mostly plutonic rock and their grain sizes are larger. So when they will break the individual grain, they will come out of that. Whereas the basic rock, basalt is a volcanic rock, which is a fine grain rock and cannot dissociate its individual grain, and it will dissociate in the form of fragment. So a basic rock will more supply the lithic class, whereas an acidic rock will more supply a mineral grain. It is all because of the size of the grain involved and the plutonic and the volcanic origin of the rock. That is why it is happening. It is not that it cannot. No, it cannot. Why? Question is, acidic rock cannot. Acidic rock separate हो जाते हैं, basic rock नहीं हो पाते हैं. But क्यों? Question वो है. Question है वो तो ठीक है जे नहीं हो पाते हैं. Now, grain sizes. Now, question. So there is an original bias. The acidic rock and the basic rock, there is an original bias of the sizes that they will produce. That is one of the reasons that we can now well understand that the different rocks they generate the different kind of sediment. But even then, if they are hydrodynamically separated, then somewhere those separated grain we should have got. If they are hydrodynamically separated, that is not permanently lost. So if I do not get in nature anywhere those grain sizes, then the possibility they are hydrodynamically separated and not represented in the depositional site is not a valid proposition, because they are lost, they are not lost forever. Rather, another thing which is more important, that is they are fragmented during transport. This is more valid, and there are different processes of fragmentation that people have talked about, which basically reduce the size of these grain sizes, and these grain sizes are least represented. Now, what are those processes of fragmentation which basically cause it? The first thing that we get, the abrasion. Second is impact. Third is grinding. These are the three major processes of fragmentation of the grains. Fragmentation of the grains. Now, what is abrasion? The abrasion is removal of edges and corners of the grain as it moves as a bed load. Removal of edges and corners of the grain because of its effect, because of its contact and its effect with the ground and its shading of its edges and corners. This is what we call the abrasion. What is impact? Impact is when a larger grain, it gives a thrust on a smaller grain. Suppose it is together a boulder, a cobble, a pebble, a sand, all are moving. So the boulders effect thrust on the smaller grain such as a pebble or a granule and further fragmenting it. That is the effect of the impact. The larger grain pushing a huge thrust on a smaller grain and further fragmenting it. That is what is impact. And what is grinding? The grinding is the smaller grains, they are getting grinded between the two larger grains. So sand grains between two big boulders or the two pebbles, they are getting continuously grinded, and thereby they are further losing their size. So those are the sizes which are getting grinded and thereby losing the size. So either abrasion, impact, or grinding. But this I can think of for 4 to 2 mm. But what is happening in the 1/8 to 1/16 mm? Because they are very fine grain and mostly they move in the suspension. So if the grains are moving as a bed load, so I can understand these processes, they will be very well valid to reduce their size, and which will the grains they will move in the bed load, that is 4 to 2 mm, 2 to 1 mm, that is the sand, the medium sand, coarse sand, and granule, they basically move in the bed load. And there, these processes, abrasion, impact, and grinding, they basically is the reason behind the further fragmentation of the grain. But what will happen when I will have a 1/8 to 1/16 or 1/16 to 1/32? If these grain sizes they are less, then what are the processes very active there? Those processes we basically call the solution, attrition, chipping, splitting. Whatever I am writing in board is visible, na?
Yes, sir.
Yes, sir.
Okay. If it is not visible, please tell me. I'll change the pen. Now, solution, attrition, chipping, and splitting. Now, these are the processes that will be more effective when you talk about the absence of 1/8 to 1/16, 1/60 to 1/32. Now, what is solution? Solution, as you know, that the part of the grain is going into solution. So it is a suboptical affair, and which you cannot see by normal eye, but it is a suboptical affair, and it is going into solution, thereby reducing in size. Then attrition. Attrition is a process which you can see in naked eye that they are changing their shape, but the reduction in the size, it is between less than 1/150th of the grain. That means it is visible, but the reduction in size, that is very, very small, and that amount of size 1/150th of the original size of the grain, that is get reduced successively time and again. That is when this size of grain gets separated and reduced, then you call it a attrition. So chipping and splitting, these are nothing but the splitting is the breaking the grain into two equal halves. That is what you call the splitting, and the chipping is the shedding of any angularity of the grain. Shedding of any angularity of the grain. That is the chipping. Shedding of any angularity of the grain. Splitting is breaking it into two equal halves. So these are the processes that you basically get in the finer grain size. Finer grain size. Okay. Now, so what we do with the size and the provenance, and what we idea about the source of the sediment. Now we'll talk about the transportation of the sediment. Transportation. Okay. transportation of the sediment. Okay. Now, when you talk about the transportation of the sediment, we know the sediments, they get transported in three different processes. Number one is bed load. Number two, saltation. We will discuss this in detail. Then suspension. These are the three processes by which sediment get transported. Okay, and we also know that any normal distributed sediment, in a cumulative frequency logarithmic curve, of logarithmic scale, it will be plotted as a straight line. That we have discussed yesterday very well, that in a logarithmic scale, a normally distributed grain size population, that will be plotted as a straight line. Okay. What? This is a famous work of Visar. What is shown? Visar. What is shown that this is grain size, this is coarse, this is fine, this is cumulative percent frequency. Okay, so if you get a card something like this, what he basically said, that this curve, because we know if a normal distributed curve, it should be a straight line. But I am getting a curve something like a sigmoidal curve. So there are three different parts. This is one part, this is one part. It can be further differentiated into two parts, and this is another. But he said that this curve should be differentiated into this one part, and this one part. And these three different parts, they basically, when I am plotting a sample in this curve, it shows a pattern like this. And if it shows a pattern like this, then it showed that this can be differentiated into three different parts of the curve. And what these three different parts of the curve talk about? That this portion of the curve, which basically falls in the coarse grain size, and it represents a significant grain size population, that is a product of bed load. And this part, which is the finer grain size, and also it is a reasonably large population, it is a product of suspension. Whereas the middle part of the curve, which is the most restrictive grain size population, and largest cumulative frequency order, that is basically by saltation. So what he said, that a bed load transport will result in relatively coarser grain size with less sorting. Same is the suspension sediment which will be a product of the suspension movement, that will show you the finer grain size but poor sorting. What I have said, what is his observation? That what grain size character will be for a bed load transported sediment and a suspension transported sediment. Bed load transported sediment will be coarser grain, poor sorting. Suspension sediment will be finer grain, poor sorting. Whereas saltation, that will be the fine to moderate grain size and well sorting. That will be the character of the Hida, I don't come to department today. एक्चुअली डिपार्टमेंट आज सील कर दिया गया है। सरस्वती मैडम को कोरोना हुआ है और शी केम विद हर सन इन द डिपार्टमेंट, सो डिपार्टमेंट आज सील कर दिया है। Actually, it will be closed for till Monday. Okay. Okay. So, fine. Thank you. Okay. So the bed load, saltation, and suspension. These are the three different the processes of transport, and there are three different processes of transport that will result in the three different character of the sandstone, both in terms of size and the sorting. And that was the contribution of the research regarding the transportation history. Now we come on to the depositional environment. What grain size data talk us about the depositional environment? So depositional environment. Now, there are different ways the grain size data was basically people thought of that how best we can use grain size data for the depositional environment interpretation. And there are a lot of attempts. And though some amount of initial success was there, but there are a lot of problems also associated with that. I will discuss the different success story also, and I will be discussing the shortcoming of that success story also. Now, in general, what people want to do to interpret depositional environment. That is one goal. Number two, in a coastal area, the grain size data people used to use in terms of interpret the translation regression history. Translation regression history or coastal sheet history. That was the history. Number three, the sediment transfer that to decode sediment transfer history from land to sea. All these are aim. Now first start with that how much they got successful. Now depositional environment. Suppose what will be the character of the sandstone of a fluvial environment? That means a fluvial sandstone. What kind of character I expect for a fluvial sandstone? A fluvial sandstone will be, number one, it will be poorly sorted. And number two, it will have a positive skewness. Now, why I will have a positive skewness in a fluvial sandstone? Because for any fluvial system, there will be no limitation that the fluvial system will carry the sediment in suspension. So in suspension, it can carry any grain, but there will be always a limitation for the largest grain the fluvial system will carry as a bed load. So if I see Ganga and Ganga, if I see in the Bihar or Bengal, in the Patna or Calcutta, if I put a big boulder in the Ganga, can Ganga carry that boulder in this in Bihar, Patna or Kolkata? Definitely not. But the same river, it can carry a boulder if you go to Haridwar. So the limitation of at particular point in a fluvial system, there is always a limitation of the largest grain it can carry, but there is no limitation of the finer grain that it can carry. And that is why that always when you basically see a fluvial sandstone, the fluvial sandstone will always give you a positively skewed curve. And it will be always represented by a poor sorting. Now, coming on to the shallow marine sandstone. Shallow marine. What will be the character of shallow marine sandstone? It will be well sorted. And it will have a negative skewness. Negative skewness. That means there will be limitation in the fine grain size, but very little limitation in terms of coarse grain size. So when we talk about a shallow marine sandstone, then the type of the curve what I expect is this. That means there is a limitation of the fine, but very little limitation of the coarse. Why? In a shallow marine sandstone, because of the repeated churning by the wave, there is a huge wave action, and the regular basis churning of the wave sweeps away the finer grain size by repeated reworking of the sediment and leave behind the coarse grain size, leave behind the coarse grain size. So if you repeatedly rework the sediment by wave and sweep away the fine grain size, leave behind the coarse grain size, so what I should expect of that sandstone? I should expect that the sandstone should be well sorted and negatively skewed. Now, what about the aeolian sediment? Aeolian sediment. Aeolian. Now, aeolian sediment, it is well sorted. Aeolian sediment will be well sorted. And it will have a positive skewness. Now, why aeolian is well sorted? Air actually is very choosy in transporting the sediment. Have you ever seen the air is taking the boulders? Boulders hawa mein ja raha hai. Have you ever seen the boulders are going? You all would have died. Have you ever seen the large amount of mud is going in the air? No. Whenever, even when there is a storm or anything, if you go to desert, that what air carries? Fine sand, fine to medium grain sand. So air is very choosy. Air is absolutely choosy that what grain size it will carry. And if you keep all the grains, suppose I keep boulder, sand, silt, clay, every mud, everything I keep, and I allow air to work on that. What air will do? Air will just pick that particular grain size, that is the fine to medium grain size, and take it away from it, leaving others back. So what is left by the air? What is called the aeolian reg deposit, aeolian reg, REG, that will be poorly sorted. But what air will take it away from there and make its own deposit, that will be very well sorted. Am I clear? Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
So the finally what I will get, that air, aeolian deposit, that will be very well sorted, but even within the armor of the well sorting, even if you have any kind of mud, clay, though it is very nominal in abundance, absolutely nominal in abundance, that may be preserved within the armor of the sand. And that fine grain, whatever small amount it is, it may give some amount of positive skewness into the grain size distribution because it can be protected by the armor of the sand. Okay. Now, what about the turbidite deposit? It is also fine grained. It is fine grained, poorly sorted, and positively skewed. Poorly sorted and positively skewed. Okay? So, all these, when it is plotted on a singular diagram, when plotted on a singular diagram, this is a diagram what I was just discussing for some time, that the sorting and the skewness, what are the different characters of the different environment. If I plot it all together, that you have a well sorted, you have a poor sorting, and then you have a negative skewness, you have a positive skewness. So this when you plot all the different environmental products, the aeolian, it will show a positive skewness, well sorting. Fluvial from moderate to poor sorting, moderate and positive skewness. Turbidite, poor sorting, positive skewness. Beach, negative skewness, well sorting. So this is the comprehensive diagram that people talk about the different depositional environment. Okay? Okay?
सर
Yes.
सर बीच में नेगेटिव स्क्यूनेस सर थोड़ा समझ नहीं आया.
बीच में नेगेटिव स्क्यूनेस इसलिए हो रहा है that in a beach you have the continuous action of the wave. The sea waves, they are continuously reworking the sediment and taking the sediment into suspension. And when it is reworking the sediment and छन रहा है, you understand the छनना that हम लोग जो छानते हैं, so waves actually they are repeatedly taking the sediment in suspension and छन रहा है. And in the process, what it is doing, whatever the fine grain size that is available, that is being swept away into the sea. It is being taken away by the wave, and the coarser grain sizes they in a biased way that is leaving behind. So when you finally do the analysis, that your analysis will be more biased towards the coarse grain size, and that is why it is becoming the negative skew. As I told, a negative skewness means that there is no bias to the coarse grain size, but there is a bias towards the fine grain size. There is a limitation of the fine, but no limitation of the coarse. Understood?
Yes, sir.
Okay. One person who has done a very significant contribution in this, his name is Friedman. Friedman. What he did, he actually plotted the sorting and skewness of sediment. The sorting and skewness. So it is minus 2, minus 1, 0, 1, 2. And the sorting value. So this is well sorted, this is poor sorted. And what he found, that he found a separation between fluvial sandstone and marine sandstone. Actually, what he did, that he measured hundreds of fluvial sandstone and marine sandstone, and measured the sorting value and the skewness value. When he plotted, you could find that the marine sandstone, they are basically the well sorted field and mostly negative skewness, while fluvial sandstone, they are poor sorting. So generally he can show that there is a difference between the character of the two. The fluvial is a poor sorting, marine is a well sorting. Fluvial is positive skewness, marine sandstone is negative skewness. A general character difference. This is his major contribution. Now, when I talk about that this is a general character, how far I am correct in this interpretation? That remains the question. How far I am correct in the interpretation? The reason is that all your everything, it is depending upon that how you are measuring the grain size and how much you are correct in, because your skewness value, the kurtosis value, and all these values, that will be actually depending upon that how you are measuring the sizes of the grains, and because you are basically giving that data. So if the problem is with the data, all the statistical values are wrong. So how much I am sure that I am measuring the correct data? I am saying, if you are doing it with a recent sediment, to a large extent, you can measure the correct data. To a large extent, you can measure the correct data and your interpretation can be good. But problem arises when you are working with a rock and a geologically old rock which has a large amount of feldspar. If the original sediment is not a quartz-rich sediment, but it is a sediment which has a large amount of feldspar and lithic fragment. Because in any sediment, you can have mineral grain which contains quartz feldspar, and you can have the lithic fragment. If you have feldspar being a more fragile and more decomposable mineral, over the time, geological time, the feldspar decay into clay, and thereby when you are now measuring the size, suppose I am measuring the grain size of a Paleozoic rock, I am measuring it for a Mesozoic rock or a Precambrian rock, and which is a more feldspar-rich Archean rock, and there the feldspar, it is decomposed into clay. Now, if I measure the size of the feldspar, will it be the correct size of the feldspar? No. And there lies the problem, that I will measure the wrong size and then my interpretation will be wrong. So what I should do, that this grain size analysis as a way to interpret the depositional environment, that can at best be done if you have a quartz-rich sandstone. If I have a quartzitic sandstone, quartz-rich sandstone, where the diagenetic decomposition is very, very low, and quartz remain being the most stable mineral, I expect that the original grain size distribution is reasonably preserved. And if I do that, then I can come out with a reasonable conviction that I am talking a sense. But if I have a large amount of feldspar in the system, large amount of lithic fragment in the system, they diagenetically decompose. And now if I measure that, I will be actually reaching out to a wrong value of grain size analysis, and thereby all my interpretations will be wrong. And that's why the grain size analysis, though it is widely practiced even now for a recent sediment and unconsolidated sediment, it is largely discredited for the consolidated sediment and the rock record. We do it, but we really do not rely wholeheartedly on this data. We take the independent data of other sedimentological analysis to talk about what is the depositional environment, and then we match the petrographic data with that data to corroborate our interpretation. Wholeheartedly based on grain size analysis data, we normally do not give a sacrosanct idea that yes, it is the depositional environment, subject to it is a high feldspathic or high feldspathic analytic fragment bearing rock. Is it clear?
Yes, sir.
Okay. Okay. So with this, we end the grain size discussion. We end the grain size discussion. Now I will start the discussion of fluid. Discussion on fluid. Okay. Now, once we have discussed about the grain size, their processing, and the grain size, role of grain size in interpretation of different kind of interpretation. Then our next topic of our sedimentology discussion, it will be we will concentrate on the discussion of fluid grain interaction. And then we'll go into the bed form. Before we enter into the sedimentary environment, then we enter into sedimentary. So first we start with the fluid. We start with Newtonian fluid. First of all, what is a fluid? What is a fluid?
Which has the property to flow.
Property to flow. That is a fluid. This is a class 6 definition. I want a master degree level definition. Can anyone give me a master degree level definition of a fluid?
It is a mixture of liquid and gas.
It's a class 4 level. सब चुप क्यों है? फ्लूइड क्या है? A fluid is a state of matter. Fluid is a state of matter, na?
Yes, sir.
What is a solid? What is a fluid? Fluid is first of all a state of matter, which cannot be sheared. Which cannot be sheared. Can you shear a fluid? If you shear a fluid, the fluid starts flowing. you can shear a solid. There is a shear strain, there is a shear stress. I think that first semester the structural geology is already told to you. You are all aware of pure stress and the shear stress, isn't it?
Yes, sir.
And where it is? It is in a solid. Can you shear a fluid?
No, sir.
No. So fluid is henceforth, if in anywhere as a MSc student you are asked what is a fluid, what you will tell? It is a state of matter which cannot be sheared. रहेगा ये दिमाग में रहेगा ये definition. Fluid includes water and air. Neither you can shear water, neither you can shear air. Because if you want to shear, then it starts flowing. It doesn't take any shear. Now, what is the component of the shear? When I really talk about the shear, when I talk that a fluid cannot be sheared, okay, then if fluid is sheared, then what is that? What we say that what is the shearing component of the fluid? That is what is viscosity of the fluid. What is viscosity of the fluid? All these things we will be discussing now. First we start with the Newtonian. Newtonian fluid. What is Newtonian fluid? Which has no suspension in it. There is no suspension. And then what does it mean? That it will flow without any shear stress. Even if there is no gravitational control, I have zero gradient of a floor, I put some fluid will be moving. I am not putting any shear stress. I am not putting any gravitational force on it. The fluid will be on its own, it will start moving. That is a Newtonian fluid, which has no suspension in it. And if it is a Newtonian fluid, then the equation for it is mu dVdH. This is the equation. That the stress on it, that is equivalent to the viscosity. This is called dynamic viscosity. Dynamic viscosity. And dVdH, this is the velocity gradient. This is the equation for a Newtonian fluid. For any stress, shear stress, that will be equivalent to the viscosity and the velocity gradient. Okay? Now, this is for a Newtonian fluid. But the thing is that this term viscosity, that is very, very important. Viscosity is very, very important. How the viscosity is changed. As you increase the suspension in the fluid, the viscosity gets changed. Viscosity also gets changed with the temperature. So the temperature and the suspension load both changes the viscosity. If you want to change the viscosity, if you want to make the fluid from Newtonian to the non-Newtonian, only about 10 to 15% of the suspension can change the Newtonian fluid into a non-Newtonian fluid. If I add the swelling clay such as montmorillonite into the fluid, even 5 to 7% of the swelling clay can make the fluid from Newtonian to non-Newtonian. So the viscosity component and the component is completely dependent upon the amount of suspension and the temperature of it. Okay? Now, there is another This thing will come again afterwards. I will be talking about. Actually, there are 4 different kinds of fluid in nature. 4 different kinds of fluid. If I draw this diagram, this is shear strain, and this is shear stress. Sorry. Have you drawn it? If you have drawn it, then I will start.
Yes, sir.
So there are in nature, we will discuss the product of all these different kinds of fluid. In nature, we actually get these 4 different kinds of. One is Newtonian. You see, the Newtonian fluid, even at 0 shear stress, it starts flowing. And as it evolving, its density and viscosity does not change. Density and viscosity does not change. It starts flowing at 0 shear stress, and its the density and viscosity does not change. That is what is called the Newtonian fluid, for which this equation is valid. If their density and viscosity goes on changing after it starts its movement, that means either it is increasing in its suspension content or the temperature is changing, so that the character of the fluid is changing after the start of movement, and then we call it a new non-Newtonian. Non-Newtonian. We can also have 2 different other kinds of fluid motion. Bingham plastic and thixotropic. But there, the flow does not start without any shear stress. You require a shear stress for start of this movement. So there is a yield stress that is involved. Yield stress. You require a shear stress to initiate its movement. And that is what is called the yield stress. But once it starts its movement, then some fluid, it maintains its density and viscosity. Then if you maintain the density and viscosity, then you call it a Bingham plastic. That is behaving like a Bingham plastic. You see, Bingham plastic we use for different kind of structural experimentation. Why? Because we know what is the yield stress by which it starts its flowage. So if I put that yield stress, that is a measure, I know. And it will not change its density and viscosity when after it starts its movement. So all my other parameters, what I will change, I know these parameters is causing that kind of effect. Because it, on its own, the fluid is not changing anything. And then if after the yield stress, the fluid changes its density and viscosity, then you call it a thixotropic. So in nature, these are the 4 different kinds of fluids. Whether you talk about the air, you talk about water, you cannot have any other character of the fluid. These are the characters of the fluid. यही चार कैरेक्टर फ्लूइड है। Now I will be discussing mostly for the Newtonian fluid. We will discuss the non-Newtonian and other fluids afterwards. When you call this is the Newtonian fluid, and the Newtonian fluid, it can be either it can flow in a laminar way or it can move as turbulent. What is laminar? When the flow lines are parallel to the surface. What is turbulent? When the flow lines are not parallel to the surface and you get the eddy. Eddy. That is turbulence. And we know what is the parameter? That is the Reynolds number. That is rho Vd by mu. Rho Vd by mu. That is the density, velocity, flow depth, and viscosity. If this is the boundary is 2000, if it is more than 2000, that is turbulent, and less than 2000, it's the laminar. Now let us see. I have a fluid which has a density 1 gram per cc. And it has a viscosity 0.01 gram centimeter second. 0.01. So if I put a flow which has a density 1 gram per cc and a viscosity 0.01 gram per centimeter second, if I put this data into this equation, then what I get? 1, that is the density Vd by 0.01. This is equal to 2000. That is the critical value. So what will happen? That Vd equal to 20. Vd equal to 20. That means if I have a velocity of 1 centimeter per second and the depth of the flow d, it becomes 20 centimeter, the flow turns turbulent. If I have a velocity of 1 centimeter and the depth of the flow becomes 20 centimeter, the flow turns turbulent. And that's why most of the flow in nature is turbulent. Most of the flow in nature is turbulent. Understood?
Yes.
Yes, sir.
Okay. And what happens when you have a turbulent flow? You generate the eddies. You generate the eddies. And if you generate the eddy, then eddy is create another viscosity in the fluid, what is called the eddy viscosity. Eddy viscosity. That is another. And then in a turbulent flow, this equation then turn into mu plus, this is the eddy viscosity, N is the eddy viscosity dVdh. Okay?